So I'll be talking a little bit about VMD, mostly kind of an update of what's happened in the last 2 years since I landed a pretty major change. The title is, 2 releases later, but it's actually, realistically speaking, closer to 4 because if you were at EuroBSDCon in Tokyo almost 2 years ago, whatever it was, you might have seen the first part of this talk where I started talking about the initial redesign I was doing. I gave an update in Ottawa, not this year, but last. And this is kind of a recap of all the things I found along the way, kind of lessons learned. So I can go a little bit deep into some areas if people have some questions later on. I'm going to try to keep it a little bit high level because I know for a fact most people are not hacking on VMD in OpenBSD. Because if you were, I would be very grateful and I'd have more help. A little bit about myself, if you didn't pick it up from the commentary about Quebec. I live just south of Canada in the state of Vermont, if you're not familiar with U.S. geography. It's about 4 hours north of New York, about 3.5 hours northwest of Boston, somewhere up there. I'm a 40-minute drive to the Canadian border, so I like to think from it. I'm not originally from there, I'm from the Boston area. My presentations always feature pictures of my dogs, primarily, so you'll see Maple and Moxie. Maple's 8, Moxie's now 3. They're not with me on this trip, unfortunately. And also their dog friend, Fritz. So, covered a little bit about this already, but kind of the area that I'm going to focus on is really the plumbing of VMD, like the really unsexy part, where I found a lot of things that need love and care and fixing. That by making VMD multi-process when it comes to VMs themselves. VMD itself was multi-process to begin with. But now, if you run a VM under VMD, you actually get devices emulated as their own independent processes. They all talk to each other through IPC. And this is the area where things were really the hardest to redesign VMD to be more modular. We're going to talk about basically the good, the bad, and the ugly. So first, what went well? What lessons did I learn? Where did things start to come apart, and where were things kind of unexpectedly horrific in my experience? And then I'll kind of close this talk with a little bit of a kind of preview of what I'm thinking of working on next, time permitting, mostly as a way to kind of motivate me to keep doing it and put it kind of, give you guys an excuse to harass me about where those things are in the future. But first, if you never saw any of those previous talks or you haven't looked at the paper I put together for Tokyo 2 years ago, what do I mean when I'm talking about multi-process? So this idea came to me mostly from tinkering on VMD and VMM for quite some time. Hypervisors or VMs or the infrastructure powering VMs are fantastic targets if you're looking to break things or steal things or just do things, because that's basically what the entire cloud computing world nowadays is built on. All the big cloud vendors basically have their own spin of some hypervisor, whether they wrote it from scratch, where they derived it from something else. And they spend a lot of time hardening this infrastructure, primarily because they need to have this multi-tenant cloud to make it look like your VM is special and unique and individual, even though you might be sharing compute with somebody else. And then most importantly, they need to move that thing around. Whether you know it or not, they can actually move your workload seamlessly behind the scenes. VMD can't really do that, but they can do it. Some CVEs that are particularly of interest when talking about hypervisor escapes. So usually what people are trying to do is they can get onto the infrastructure and they usually want to break out of the virtual machine. People tend to use VMs for, I'll say sandboxing. It's a weird term in this case. And some people think, okay, it's safe, I'm putting this program in a VM, it can't do any harm. Obviously, we all know that's a little bit naive. Some of the best ones have been, in my opinion, from about 9 to 10 years now, related to device emulation in QEMU. So the floppy disk controller, which I bet most people who spin up a VM in Linux, who, they might be using whatever GUIs wrapped around libvirt or whatever these days, they might actually boot up some emulated hardware that they don't need, including a floppy disk controller, just because. But these devices lingering can actually prevent or provide footholds for people to break out of the guest, manipulate the state of the host. So there's some cool, these are actually links. Once I publish the PDF, you'll be able to click on them. But basically, the theme is the same. You know, there's some emulated device as a guest workload in the VM. You get to talk to that device, because that's how you communicate to the outside world. And if you can get that device to do dumb things, like a buffer overflow or stack overflow or something, or misemulate writes to memory somewhere, you can now control behavior on the host. So the general idea from like a threat perspective is, okay, it's not like you can't not provide devices, because then it's not a computer you're emulating anymore. What's the point if there's no storage or network? Like, how many people are running a VM with zero networking? Maybe on your local machine, but it's very low value. You're not going to be able to build a business around that. People have to put stuff on the internet. So how do you really mitigate the blast rate of this stuff? OpenBSD is not immune to it either. I remember my first hackathon for OpenBSD. I showed up with a plan to do something. That plan got thrown out the window immediately because somebody had reported, the ability to inject packets into a VMD instance to cause buffer overflows. Like, oh, cool. Now we get to tinker in this code that I didn't want to touch. So I saw, working on this stuff and being a self-described lazy individual, I want to make stuff not break as much as possible, because I don't want to have to come back and fix it, because I'm lazy, and I do this mostly as a hobby. I'm not paid to work on OpenBSD or VMD. And I came across, once upon a time, QEMU had a talk given by some Oracle engineers who split QEMU out into multiple processes. Now, I think their intention was different than doing security hardening and whatnot. It was maybe more about shared devices for performance efficiencies and things like that. Because, like, imagine if you created like a network process that tied all the VMs together for them to exchange data as if they're on a private network. Maybe there's some efficiency to gain. But you can also use it for hardening. The talk was given. There's some good patches that were posted and merged in, and I've never seen or heard of anyone ever using it. I'm assuming since they're Oracle engineers, Oracle Cloud uses it. I don't know if anyone here works at Oracle and can corroborate that. But you go to the wiki page, and it's documentation about the design, not about how you use it. And you basically have to start a separate process and link all these things together, and it just looked like hell. Which is really not how we like to build daemons in OpenBSD. Say what you want about, the bugs or fixing the code itself, but usually from a user perspective, we like to keep it as simple as possible. So the general idea was to take the existing VMD design. So I wasn't around during the initial design and delivery of it, but the architecture of VMD traditionally has been like a lot of the privilege separated daemons in OpenBSD. You've got the kind of primary parent process, in this case called VMD in this diagram. It'll do this dance of fork and exec, fork and exec, fork and exec to create a bunch of child processes. And each of these is usually specialized to do something, because then we layer on different privilege dropping techniques. So there's a control process which handles if you're using vmctl to start a VM or to connect with a console. That thing will talk to the control process. The VMM process talks to the kernel to actually start or stop a VM, to run a vCPU, for instance. Privilege process, it's kind of an appendage these days that I think all it does is a single call to do some sort of network interface address assignment or something like that. I can't even remember. AgentX is relatively self-explanatory if you know what AgentX is. But then the general idea was the VMM process would really be the one that forks and creates a VM that you'd be running. Now, originally, if you started up a guest, you would get a single process, and that would do everything. It would emulate the disks, the network, the CPUs, all this stuff. And for the longest time, and I still think to today, VMD is the only user land ship base program that uses pthreads. So if you think about how odd that is, because it's not odd maybe in other BSDs, but in OpenBSD, multi-threading is usually not the design used for building any kind of base programs. So that kind of makes this little oddity to begin with. It makes it hard for contributors, makes it hard for people to debug. And it was actually the reason that I started playing with VMD and hacking on it, because it didn't work half the time for me. because there were race conditions, because it was multi-threaded, and you could just have your Linux guest just poof, crash, gone. And apparently that was enough to trick me into working on it, and here I am today. So what I did previously, around 7.4 or so, was, okay, so that VM is one process. There's a lot of complexity in there. Taking the inspiration from the QEMU stuff, so this wasn't solely my idea. It was, okay, let's take these devices, especially the commonly used ones, so the block device and the network device. Pretty much every guest will have usually at least one, if not both of those, maybe even multiple. Split those out into their own separate processes and let them only do what they need to do. So if I'm a disk device emulating a hard disk, I just need a file descriptor that points to the file or files on disks. It might be multiple file descriptors, really. QCOW2 images can have all sorts of layers. But if it's just a raw disk image, I just need a file descriptor to read and write and access to guest memory, and then some ability to be kicked in the head when the vCPU is trying to read or write to one of my registers. So that was really all the work that I presented previously. So nowadays, the actual architecture reflects everything here. I did a weird twist and that tweaked my back. So now, like, if you have two network interfaces, they actually fork an exec off the VM process. They end up using pledge and other kind of capability restricting like approaches to only do what they need to do. So now the idea is if somebody finds an exploit like they did for the DHCP emulation in VMD, and they bust out into the host process, they'll end up here, and this will have a lot more restrictions than one step up above, because the VM process needs to actually run the vCPU and do all these other things, and now we've really got to separate it out into just individual concerns. So that's all generally a nice design. And this was really my goal, summed up basically in this one slide. So, what really impact would an end user have? So a lot of people use OpenBSD and just upgrade every release, never really read the release notes, don't even necessarily know what's changed. And in general, you shouldn't, I don't know. I know I'm being recorded, but I mean, you shouldn't have to read the release notes, so you should be able to upgrade. I mean, sometimes you're gonna have to go in and change something because we have to deprecate stuff from time to time. But the world shouldn't come crashing down because you did an upgrade. You shouldn't have to learn a bunch of new command line arguments. VMD was already designed to be simple. You can start a VM just by saying vmctl start, and they say, okay, I want -L is a local network interface. C is give me console access right away from that process. D is a disk, and here's my disk image. M is the amount of memory I'm going to give it, and then the VM name. Which, if you use QEMU or even some other hypervisors, like this is simple. Like it really doesn't get much simpler than this. When I landed those changes, if you can tell, if you diff these things, there's no difference. Like that's the exact same thing. So you would benefit from the redesign without having to learn anything new. So that went well. I think I don't think I received any angry emails or complaints that people's scripts or their habits of what they type changed or broke. And then we also were able to do some better, cooler things as a result. So when all that stuff was crammed into the one VM process, it was a lot to wrap your head around. The same process doing networking and disk I/O and vCPU emulation, all this stuff, it's a pain in the ass to get somebody interested in fixing or tweaking or enhancing. So our initial VirtIO implementations on the device emulation side, they did the bare minimum. It got things working, and there was a lot of room for improvement, but making those changes was extremely haphazard. You had to really know the code, unfortunately, and how to sift through what you didn't care about to get to what you did to make the change. And quite frankly, it was really daunting, probably the worst in terms of, I'd say it's probably in the top three, probably with OpenSSH and SMTPD as being probably the scariest things for somebody to come by and touch. Although I'm sure we want people to touch other daemons more frequently as well. But by splitting everything out, it allowed even me, who had been working on the code for a long time, to then focus and say, okay, where can we make stuff better? Now I got all the network emulation stuff in one file. It's not like surrounded by all this block I/O stuff and all this other emulation. And that's where a lot of performance enhancements came from. So I started down this path of maybe hardening VMD, but in reality, this ended up being a big kind of performance boost. So by splitting out like the disks in the network, I was then able to read the code better, quite frankly, and found all these inefficiencies. We were just copying data from buffer to buffer to buffer over and over again. So if you see any kind of latency improvements in the last 2 or 3 releases, it's probably entirely related to changes that came as a result. So nowadays, if you're using raw disks, we're actually doing zero copy, where the guest gives us some buffer of data to write to the file. We're no longer copying it into some intermediary buffer in VMD and then writing it out to the file. We're just going directly from the guest memory into the file itself. And then the best thing was most of these changes were net negative, actually deleting code. And I went back and I looked at my diffs I committed, and at least for the VirtIO block rewrite, I mean, it was practically a rewrite. It was actually 80 lines shorter, which is pretty substantial when you look at that file itself. And then since it was a lot more efficient, we're not copying stuff around, the host CPU utilization actually went down as well under load. So, and if you run guests that are not OpenBSD, you actually see pretty good benefit here, because Linux guests make better use generally. I mean, we can't support FreeBSD yet or NetBSD fully. I can tell you over drinks what needs to be done. But Linux does a better job of using multiple buffers with VirtIO to be able to push more data faster, basically, is the net of it. And VMD was now able to take better advantage of it. So your workload in Linux under OpenBSD actually improved probably more noticeably than OpenBSD guests under OpenBSD, which the Linux guests were actually already pretty performant. The other cool thing was the network emulation. If you ever did any heavy network stuff with VMD, so like if you had an OpenBSD Amsterdam host, and you're trying to do any sort of streaming of media or anything that you'd notice latency spikes, like tail latencies. If you weren't using maybe UDP or something like that, that device emulation was entirely single-threaded. So sending data over the network, receiving data off the network, dealing with all the inter-process communication from the VMD process or the VM process, all one single event loop, which you basically could, if you did it right, you could starve one side of the transmitter-receive networking just using iPerf3 or something, if I remember correctly. It was very simple to do. Now everything was in one file. It was a lot easier to now introduce multi-threading. If I had done that before, it would have been an absolute nightmare. I would not have signed up my personal time to add multi-threading to VirtIO networking without it being in a dedicated kind of process. So now it's a lot easier to modify this stuff. So if you're not aware, VMD actually has its own kind of built-in DHCP service. So when I did say -L on the couple slides ago, not only does it gives me an interface, but it gives me a quote local interface, and it sets up, if you send a DHCP request out on that interface from the guest, we intercept it. We're actually doing packet inspection on those packets before we put them out on the network. If it looks like it's DHCP, we intercept it, process it within the VM VirtIO network emulation, and we'll inject the response into the receive side. So it's actually a pretty interesting place that if you wanted to do kind of weird hacking on kind of packet intercept stuff, the pieces are a lot more accessible now. So that was all. Those are all positive, happy things. I mean, all this stuff sounds like it went well, but that's really not the case at all. The first thing was really all of the IPC plumbing here. That's Moxie when she was little, sniffing Maple's butt. I think it's appropriate for this slide. this is an area that I think could probably be simplified, but in order to have all these separate processes for emulating a VM, there are all sorts of different kind of messaging patterns that need to occur. And really, they kind of fall into two categories, synchronous and asynchronous. The most, probably easiest to understand synchronous channel need is if I'm a vCPU and I go to read a register using port IO. So we don't emulate MMIO yet with VMD. So we use port IO. We only support Intel-based devices. So I'm actually using an in or an out instruction in this case from a port. That CPU is basically going to assume it's going to get data back. It's basically a request reply pattern. Like it has to block. Like it's not able to submit a request and then be notified via an interrupt or something or poll for the result. So basically, we have to have the vCPU thread in the VM process wait for another process to receive that message saying, hey, somebody's trying to read this register. Go get that value. Reading a register might mutate state based off of what register it is. So handle that. And then, oh, you need to send the reply back because then I need to give it back to the vCPU thread. And this is a little bit of a pain in the ass, to put it bluntly, because if you've ever looked at any of the heavily privsep daemons in OpenBSD built in the last 10 years or so, I think, so HTTPD, RelayD, VMD, I'm sure there's others. They all use a combination of libevent, which is in base, libevent 1 dot whatever, can't remember what we have currently, and then a framework called iMessage to do the IPC messaging. And it's all basically designed to be asynchronous. So by doing some synchronous blocking and communication mixed in with this asynchronous event loop stuff, you get real interesting friction and some really heinous code. So that was really the biggest headache. The asynchronous stuff, really not that bad. It actually got a little bit better because now if you wanted to say pause, let's say you say vmctl pause and you want to just suspend a VM and say stop processing, we now actually broadcast the pause event out to all the child processes. So if you have like 5 network interfaces, I don't know, they'll all get a pause message and we wait for them all to respond and say I'm paused, and then we kind of quiesce the whole thing. So this is kind of a visualization of that headache and where this is the most problematic. I drew this like 2 years ago on my iPad on a plane. So I'm not an artist and my handwriting is very bad. It's actually probably not too bad here. But the general flow, so like if you want to think about how something like that simple register read gets emulated. So you'll have a driver in your guest somewhere and it says, okay, I want to go read the status register for this VirtIO device. So it does some sort of operation, some instruction, causes a VM exit. We fall out of the kernel into VMD. VMD looks at the thing and says, okay, it's trying to read this port. This port I know is associated with this VirtIO device. This VirtIO device is this process over here. Go grab the channel to that process, send an event down that way. And now I got to wait. So it kind of goes around this loop. So we get kicked out of the guest, talk to the vCPU. It might send, in this case, it might send something over the synchronous or asynchronous channels, depending on what type of operation it is. The device will do the emulation, and then either synchronously or asynchronously reply back. If it's asynchronous, usually it'll be like, okay, I've finished using all the buffers you gave me. Now I want to send an interrupt. So what happens is the device process actually sends an asynchronous message to the VM and says, hey, go kick this vCPU, go generate an interrupt for us. There's a lot of interconnects and moving pieces. So this is where it's kind of starts to get pretty ugly. To kind of make the ugliness a little better, that's Moxie as a puppy, I think, back 3 years ago, I think now. The way all of this is really possible is a little bit of a hack in OpenBSD from before I started working on it. So all of this is made possible by shared memory between processes, effectively, that and then the IPC channels. So a guest has memory. In that example, it was like 8 gigs of memory. So when you start up a VM, it goes and allocates 8 gigs of addressable virtual memory. And what happens is there's a special VMM device, IOCTL, that if you have permission to, you can say, if I have a file descriptor open for the VMM device, I can say map the guest shared memory into my address space. So this is used by these processes when they split off, because they're forking and execing, and they have their own new address space, a new layout, and all this stuff. So they need to find a way to be able to read and write to the guest address space, because that's how device emulation works effectively. So we had to add not this interface into the kernel, but then had to really take advantage of it extensively. My first implementation of this was horrible. It tried to use the shared memory framework, which used files and things like that, and it just leaked things. I don't know what was wrong, but it sucked, and I had to redo it all. And that took weeks, I think, of time. So if you use snapshots during that period of time, you might have noticed like some files appearing in /temp and running out of space in /temp, because I didn't fully understand the implications of using the file-backed approach of shared memory. But now it doesn't do that. It's a lot easier, but this is still a bit of a pain. Before every device can drop all its privileges, it still has to be able to do this. So it needs to know what that layout looks like, needs to have the file descriptor open to VMM, and then be able to make this call. The bigger problem wasn't really using that interface so much as all the new stress put on the kernel. So earlier I mentioned VMD is the only thing that's multi-process in the base install. VMD is also the only thing that uses that devVMM shared memory call. So it's the only one doing it that way. So we're a special little child, that has special privileges, it seems. Maybe privileges isn't the right word because it implies a lot more than probably mean to here. But we're basically stressing the kernel and all these other subsystems in ways that other programs in the base are not, which means we being VMD users and hackers, find things that people haven't found yet, especially as things are changing in OpenBSD. So I didn't set out to read UVM or PMAP code. I just wanted to hack on VMD. But as a result of all of this stuff, I had to, because all that shared memory stuff started putting weird pressures on the virtual memory subsystem in OpenBSD. If you want to get into the history of OpenBSD and some of the code, I mean, you can go look at UVM files. It's in sys/UVM or something. A lot of it comes from around the NetBSD days before the project forked off, and you'll see code comments in there that will make you kind of shiver, because they're probably from 25 years ago of someone should come back in here and look at this, or guess what? I don't think anyone did. So, and NetBSD and OpenBSD have diverged a lot in UVM. I think FreeBSD uses a completely different virtual memory framework these days. So NetBSD is the only one that I think we share some common base with. But if you look at the two side by side, they're very, very different in the kind of ways they've grown. And there's a particular memory corruption I've been chasing now for 2 years, at least 2 years. So if anyone in this room has a dual Intel Xeon machine that is doing nothing, or you don't have any use for 30 days or so, I would love to bang on it, because it's the only architecture that will surface this particular memory corruption. We've had some folks working on pushing kernel locks around and unlocking things, and this has only gotten easier to find with multiple processes sharing address space or subsets of an address space. Because what happens is during teardown, the teardown of these address spaces, it's not supposed to be racing, but it seems to be. And I'm finding these fun things where we're corrupting pools of kernel memory, and it's not good. It only happens on Intel dual socket Xeon. It doesn't happen on AMD. I spent money to boot up a dual socket AMD server in some cloud somewhere, like bare metal, to bang on it for 30 days and did not break. Can't do it on my laptop. So These are still some of the ghosts that I'm chasing that have actually kind of been more prevalent since this kind of redesign in the last 2 years. And more than once, I've been convinced that I've solved it, which makes it even more painful when it surfaces again. As of right now, I'm not of that mindset. I know it's not solved, but you asked me like a couple months ago, I was like, oh yeah, definitely, I got that. It's fixed now. It could be related to this one area that if you get a couple Guinness in me, I'll probably go on about. Intel is special. And if you ever have to do low-level stuff and look at like AMD versus Intel programmer manuals and that stuff, you'll realize that there's a very different mindset at Intel than AMD in terms of design for us, the end users of the hardware who are writing software. Part of it is their virtualization extensions are older than AMD's. I think part of it is also they kind of design fundamentally differently. Everything you do on an Intel machine to accelerate virtualization sucks. It's inefficient by design, and it creates more overhead for operating system developers and maintainers than AMD by far. And this is an area where, like, if you like pain, you can go look at. You don't even need to write the code. If you just go to either OpenBSD or NetBSD or FreeBSD, I think the NetBSD code is actually a pretty good example to look through. The type of handling that you have to do with Intel versus AMD is just insane. So the big thing, not to go into all the details, but effectively every process usually has its own address space. An address space is usually described by some sort of page table mechanism. That's a design now that's across multiple architectures. So it's not unique to Intel or AMD-based stuff. What's unique to Intel is when they decided to do nested page table virtualization or acceleration or whatever they want to call it. Sometimes it's called two-dimensional paging, I think, although it's not frequently used. Nowadays, people just call it nested paging, I believe. I think that's usually what they call it. But basically, Intel decided we're going to take the specification for Intel page tables. We're going to make slight changes to the ones specific to virtualization, such that if you ever load a Intel, it's called an EPT, extended page table, I think is what it stands for. If you ever accidentally load that onto the CPU like a regular page table, the bits aren't going to line up right and something's going to break. AMD did the opposite. They said, okay, here's the design for virtualization. Here's the design that's been around for ages now for actual regular hardware. Let's just make sure they line up okay and you don't explode if you accidentally load it onto the CPU. And that right there is the cause of so much suffering in my current life. I've got a lot of diffs floating around that aren't going to make the next release in the next month or so. But if you're on the list, you'll probably see some stuff going on about new IPIs to do flushing of caches and other things that I need to do, because in Intel land, you have to do everything again, is basically. It's like, oh, you built an operating system for hardware? That's great. You want to do virtualization on top? Now you got to add an extra layer of your operating system to deal with that. So if you work for Intel in this room, please don't identify yourself. So I mean, the real takeaway here is that as much as there's been pain and suffering and we've kind of surfaced a lot of bugs, from the end user perspective, if you just run VMs on your laptop using OpenBSD or you're running them on a server somewhere, the impact has been extremely minimal, if not non-existent. I mean, what you see really is different system utilization. So I'm running just a local VMD instance with a OpenBSD guest and a Debian 12 guest, just to kind of illustrate how things shake out from a process and thread perspective. So nowadays, you'll see if I remember the commands here, if I don't display threads, this is just filtering down to just VMD or processes with VMD in the name. So you'll see things like, VMD Puffy here is the OpenBSD guest process. But you'll see Puffy/VIO block 0, which is a separate process that's emulating the block device. So anytime I do disk I/O, that's the program that's actually doing the emulation, working with the file on disk. I could shoot that thing in the head, and yeah, this whole thing might come crashing down. But the nice thing is now with VirtIO, technically, we've had a bug recently. I can't remember. Moritz isn't here. There's a particular networking scenario somebody encountered, one of the developers, and he's like, my network interface stopped working. And previously in VMD, I'm sure it would have broken the entire VM. Now it just kind of screws up a single emulated device, which is a lot easier to reset now that there's hooks to do that. And if you look at the threads, you'll now see that not only is it multi-process, but now there's a bunch more threads. So really taking advantage of multi-core machines and emulating, some trivial hardware. OpenBSD is all single processor, so maybe this is overkill. But I've got a 12-core, 16-core machine here. Why the hell not use all 16 to run my 2 guests? So you'll see the multiple network processes here, or threads rather. The names, there we go. I can never get these right. But now you can see there's one particular thread that's related for transmission. So it's the one that will take the data off the vert queues from the guest and put them out on the wire. RX is the one that's listening to the tap device to take packets into the guest, and then there's going to be another one there that's like the main event loop. And you can see the vCPUs as well. So it looks a little bit more complex from like a system administrator point of view of monitoring the machine. But from a code and design perspective, it's a lot, I would say, cleaner, a lot simpler. It's made my life easier, which in all reality, that's what matters, right? So looking forward, if you see me talk again in the future, what might I be talking about? I mean, this has consumed the last 2-ish years of my life. It's been the primary focus of what I've done other than a lot of housekeeping and cleanup of the code. I don't think there's any other major changes I've done other than what I've just showcased. We are looking, or I am always looking for more hands or help. I just covered the microphone. I'm sure that sounded great. It's really only a couple of us that hack on VMD, none of us full-time. Not that I'm looking for anyone full-time to do it, but if this gets you interested, definitely come talk to me. I mean, this is sort of the to-do list. This is the number one bullet point is always what people ask about, when can we get multiprocessor support or SMP? It's coming in baby steps. It's just, I'll be very brutally honest for once, it's just not that exciting to me. It's exciting to have that capability. Building it is not the exciting thing. To me, I like more of the, the weird plumbing stuff. So convincing me to dedicate what time I do have to it is going to take a little bit of bribery, maybe. I don't know. ARM64 is probably more likely because myself and another developer, at least, that would be working on this do have hardware now that supports doing this. We have done the initial kind of machine-dependent, independent refactoring of VMM and VMD. You may or may not have seen a bunch of commits that occurred that all they did is shuffle files and code around. That's all it is. You can technically compile and run VMD on ARM. It does nothing. It just exits, but you can compile it. So that's step one. A couple of years, maybe we'll get there. Where my head is at right now is this thing that doesn't exist yet. I'm calling it IPC Gen. Because all of the pain I always suffer from hunting bugs in VMD is always related to that horrible plumbing diagram I showed. And that's just the device emulation part. There's also channels between all of those other processes. And if you look at the flow control for doing something as simple as starting a VM, you run vmctl. So that's one program that talks to the control program through the Unix socket. That sends a start VM request with a bunch of parameters. That then forwards it to the VMD process. And then let me see if I can do this from memory. That will then, I believe, check permissions to see if that VM not only can be run by that user, but if it exists already, and basically look for conflicts in the global state. It will then forward that message on to the VMM process to say, I'm starting a new VM. It needs to check its own little state. And then it's going to start sending off the same message to other processes, to open file descriptors, to possibly other files and all these things. These are all individual messages that get sent while your little client is waiting for the response back. I don't even know if we wait, to be honest. I think you just get told if it failed right away or not, not if the guest actually started. So all these messages have to ping pong around, and keeping that mental model in your head, if you weren't in the code, is almost impossible. And so my idea is that all of this is very descriptive. It's a graph. I used to work for a graph database company. Everything's a damn graph in my mind now. I drank too much of the Kool-Aid. All of that communication can be defined in its own little, language, basically. All the plumbing underneath is always the same. There's so much boilerplate in VMD, so much boilerplate. It's all like this event response type thing. Okay, I'm this process. I get this event. I do this. I send this response on success. I send this response on error. The plumbing shouldn't matter. The plumbing's there. We always generate the same event loop format. We always do the same iMessage, reading and writing, buffer filling, emptying dance. There's nothing fun or sexy there in terms of uniqueness. So why not describe the plumbing in something more dedicated? Every daemon has this problem. HTTPD, RelayD. There's common denominators here for those that know it. There's a lot of copy pasta. So pushing this behind a code generator, making it so, okay, now somebody's working on an event handler versus changing the plumbing. Or if you do change the plumbing, now you are generating the boilerplate, that type of thing. This might help future daemons, and who knows? Maybe someone will decide to write an IMAPD with this and make my life better. You never know. So I did want to close. I know we only got a couple minutes, but there's another good talk about VMD tomorrow, about some of the new stuff going in lately related to secure computing on AMD platforms. So if you use AMD and not Intel hardware, and you use VMD, you might want to check it out, because I think most modern AMD hardware would benefit from this. So I think it's same room, 4 o'clock tomorrow. But with that, I close with one other picture of my dogs. First here.
Does your work allow for direct disk access?
No. So the question is around direct disk access. I'm assuming you mean pass through like a raw device to the guest. Technically it does. However, it's not possible in OpenBSD because we do not allow passing file descriptors to raw devices. All of this is based on passing file descriptors through sockets. And the kernel explicitly forbids that type of file being passed. It's like a couple line change that could occur, but there's a lot of debate that would need to occur around supporting passing descriptors to raw devices. I tested it. It worked. I did a full install with a USB device plugged into my laptop where I used the raw USB device and it worked. But it requires a kernel hack.
It seems suboptimal that we have buffer cache in VM and in the...
Yeah, so it used to be, I don't know if it still is in Linux world, but like 15 years ago, I think the general advice was to like tell the OS, like in the guest, like don't buffer I/O because it's being buffered by the host. So I don't know, maybe that's the simplest answer. I don't think there's much of a performance gain in the short term without maybe something like that. There was another question?
Yes. Now that we have Voutila GPU in the base as a driver, I don't think we have a device in VMD.
Right.
Wouldn't it be great?
So the question is around, would it be great to have VirtIO GPU device emulation? I think the answer is generally yes. I haven't had a need for it, so I haven't written it, but the only gotcha is I don't think our bootloader or I think CBIOS, which we use, might support it. I don't think our bootloader does necessarily. So you might not get an actual display of the bootloader. But if somebody wanted to write a new device to emulate, that's probably the most likely one, is something to do Visual Console. The VirtIO GPU spec is not very complicated. VirtIO itself is not too complicated when you read the spec enough. I just personally don't know anything about graphics. Graphics and networking are areas I really am ignorant of. I like to keep it that way. So if someone else wants to do it, I'm more than happy to review it.
So you're
Yep. That's sort of it exists as a thought experiment, and I've kind of written drafts of what I think the language would look like for VMD. And my plan is, before I write any code, would be to extend that thought experiment to the others to see, okay, if we were to rewrite HTTPD or RelayD, what would this look like, and would it simplify things? Because if it doesn't, then I don't know if it'll be worth my time to create tooling just specifically for VMD. But who knows? Yep. Yeah. I think the areas that I want it to solve are visualizing the communication flow in a way that's concise, so anyone can just read it and understand where the messages go, and then encapsulate the file descriptor passing, because that is one of the more opaque things to understand about. Because, for instance, there's a way you can actually provide an override boot kernel image using vmctl. Now, the vmctl process will open that file and then pass the file descriptor. Now that file descriptor needs to get passed around all these little hops. So knowing where it is and where it's going and what it represents, that's one of the reasons why there's so many messages that get fired off during the start VM, because by design in the Unix world, you are only going to pass one file descriptor at a time, right? You're never going to need to pass a dozen for a QCOW base image set. So like, iMessage does one file descriptor per message max, and you just get all this ping pong going on. So there's actually a lot of errors that silently will occur in VMD that you'll never get a message for, because there's just too much communication for us to do full request reply. There's a lot of optimistic assumption that if we get this far in this communication, we're not failing. So that's why you get these obscure messages from vmctl, because it has no idea what happened. So that's where I'm kind of thinking. I'll publish my consulting rate on. So, not that I'm aware of. NetBSD, FreeBSD, and Linux all do the legwork to properly handle EPT, PMAPs, and flushing and all that stuff. It's just error prone. So like you can put that in the same category as memory mapped IO emulation as being error prone. I mean, there was just a FreeBSD CVE in the last month or so about MMIO emulation having a bug that allow a guest to write anywhere in host memory or something, or the host process memory, virtual memory. And so that's like one of the fears of where do I put my time on something that's going to create a bunch of foot guns and things I have to maintain. Like, I want to do the least risky thing that I can enjoy doing and not necessarily walk away from, but I don't want to create a bunch of bear traps to other people step in. That's why we don't have SMP yet.